5-minute warning in the microphone. So, but you can take it away now.
All right, cool. Thank you. Thanks again for giving me the opportunity to talk about this. I'm sorry I'm not there. I couldn't travel to Chile. But today I'm just going to talk to you about another FUor, V900 Mon. It's a work that we've done at Concord Observatory, and some of my collaborators are actually there in person. So please ask more questions after I'm offline. Oh, there you go. Okay, so I'm not going to say by repeating many things about the variables, as you know, just to mention that quickly that there's currently more than 40 known, and of course there's more to come from Gaia. I'm sure you heard the talks yesterday. And here in Kokoli, what we do is use the high angular resolution techniques to look into their disks, and IFU to look into the outflows of the stars. We've done a fair bit of work already with VLTI, so infrared interferometry, and there's more to come in the future. But quickly on V900 Mon, if you haven't heard about this particular target before, it was discovered in 2009 by an amateur astronomer. The nebula was. It's a quite large reflection nebula, the one I showed you on the title. And based on the light curve, as you can see on the bottom left, this particular object erupted sometime in the 90s. So it's still on an outburst with a minor fading around 2018. And that's more or less all the data we have for now. There's no more recent data in that. And the plot shows the blue, green, orange, and red is BVRI magnitudes. And earlier, I think the first paper on this particular target was from Lykou et al., and they found out that from the spectra of the target, it's a bona fide FUor with a very high circumstellar extinction. And this is actually quite far away object. It's about 1.2 kiloparsec. So these are not the only things that we have. So in terms of high angular resolution, of course, ALMA is an important player. And this particular target has a very compact disk. It's less than, it's about 100 AU, actually less, with a critical radius of about 22 AU. And it's almost polon, so its inclination is between 14 and 34 degrees. It's a relatively high mass for the disk, at least from the sub-millimeter observations. And it also has a very spectacular bipolar outflow, seen in 12C. And with this is in the lower right corner, so you have a very, to the east, you have a very wide structure. And to the west, it's a much smaller cavity structure, as you see in the CO maps. Now, why we care about this in particular further on, so a few years ago, when I said we had some working on MIDI data in the past, and in this particular target, it looked like the MIDI spectrum, so from the mid-infrared combiner from the VLTI, it showed, it's the plot on the right. It showed the crystalline silicate feature around 11 microns. So we thought that this might be one of the first candidate for crystalline silicates was EX-Loopy, so maybe this could be one of the first FUors that have this crystalline signature. So we asked for observations with MATISSE, which is the new imaging interferometer on the VLTI. And we managed to get a couple of snapshot observations, which means it's not imaging just like point and shoot in a way in the L, M, and N band, so about 3 micron, 4 micron, and 10 micron band. The instrument has a very good spatial resolution, so we are basically looking into at the V900 Mon distance around to resolve structures from 4 to 10 AU in the disk. So we checked for crystalline silicates and show you some of the MATISSE results. Not sure how familiar some of you might be with the concepts of visibility, correlative fluxes. So visibility is in a way telling you about the size of the source you're looking at. The correlative flux is the visibility times the total flux of the object. So it gives you an idea of what is the different flux scales as you go into a structure. So from this, we find out that, first of all, the diameter of the inner region, so about 3.5 micron, it's much smaller than 3 AU, which should tell you that the radius of that region is about 1.5 AU or even less, because it is marginally resolved. While in the N band, which have much better observations, we are looking at the structure which is about of the order of about 10 AU or much larger than that. And the plot on the right shows you the correlative fluxes, and these are ordered by baseline length. So from the top, you go to the shorter baseline, which basically means that you're sampling the outer regions of the disk. And as you go to the bottom of this plot, you see the longer baseline, which means you're sampling somewhere very close to the center of the disk. And as it happens, these are ordered from higher fluxes to lower fluxes, meaning that you're looking at something which is bigger on the outside of the disk, and you get into a smaller and smaller region towards the disk. So you're looking through in a way. Now, sorry, let me go back a little bit. I spoke a bit about crystalline silicates, but as you can see in these plots, it's not very clear if you have any at all. There is a certain shoulder, sorry, a certain slope between 8 and about 11 micron, and there is a flat shoulder at certain baselines, while when you go to longer baselines to the bottom of the plot, this looks more or less flat all the way through. And that to us means that there is some kind of radial variation of the silicate feature we can see here in the N band. And if we combined the different quality fluxes from different baselines, so you combine the two smaller baselines and then the two bigger ones and the two bigger ones until you reach the maximum baseline, which is about 130 meters. And you subtract the continuum from all of them, and then you try to join them together. So you're getting the two smaller ones, then the two intermediate ones, and the two larger ones. And this is the kind of plot you have. So you see here in blue, orange, and green is these summed average correlated spectra. And these correspond to 3 different regions. So you're looking at regions, which is the blue here, that are smaller than 16 AU in radius, and then you go into smaller than 12 AU and smaller than 7 AU in radius. And the interesting part is that in the top plot, you see a trapezoidal feature of the silicate, a trapezoidal shape of the silicate feature, and that's the blue one. Then the shape kind of changes for the orange spectrum, and then it's completely different when you go to the green spectrum below. Also, on top of this, I have we follow the same process for the old MIDI spectra, which were taken several years before. And again, for exactly the same baselines, you have a similar structure in gray, which is a trapezoidal feature, and some kind of S shape at the longest baseline. So this trapezoidal feature could be smaller grains, so something smaller than 1 micron, and further on, so we don't see much of larger grains from this analysis alone. Also, we don't see clear-cut crystalline silicates, because this is I'm not sure if the colors we show pop up, the dark red line in the middle. And there is not really a clear-cut signal within the noise. And it doesn't also look like the ISM feature that you have, the red line here. So we didn't stop there. So we thought, like, what could be the reason that you have such a difference between different spectra? One of the concepts we find is, what if you use the blue, so the longest, the larger spatial scales? What if you use the blue as a standard, and then you try to reproduce the orange and the green to fit the blue? And to do that, we would have to basically de-redden the spectrum. And if we do that and we redden the spectra, the orange line here by about 0.5 AV, you more or less fit the at a similar level as the blue line.
With 5 minutes.
And oh, sorry. And if you do the green one by about 3 AV, you more or less fit again the blue line as well. So there is some kind of circumstellar screen that must be on the core of the disk. And this is on top, of course, of the interstellar extinction you have for this target. Now let me quickly move to MUSE, where we had a look at this object with the IFU, and we were looking for a jet emission. We're looking at a spaxel of 0.2 arc segment, which is more or less the same as the field of view of the MATISSE instrument. And what we found here is in this color image, the blue here is H alpha emission. The other two are continua, the red and green. And you'll see two clumps. Both of them are aligned with a position angle of 250 degrees, which just happens to be the extension you can measure from the 12 CO maps by ALMA. So if you extend it further out, they're aligned perfectly well. The first one, although, the one nearest to the star, we don't really trust it because this is very close to a lot of scattering from the nebula. But the further out one is a clear gaseous clump. And I'll show you quickly, this is a continuous subtracted image where the clump is clearly visible. So we took spectra from both the star and the clump itself. So the star shows a typical FUor spectrum, with absorption lines. There are no emission lines in this one. But for the knot itself, which is in the orange, you see strong emission lines in H alpha, not so much in H beta. Perhaps in oxygen 1, and also in nitrogen 2 and sulfur 2. And from this, we get a density of the knot where this blue shift is emission about 100 kilometers per second. And the size of the knot is about somewhere about 1 arc seconds. And if we trust the inclination we've measured before, if we trust the position angle measurements, then this would mean that this particular knot was perhaps ejected around 5,000 years ago. So our idea was what could cause all this, because you have a knot that is at quite a large distance from the star. It's about 0.13 parsec. We couldn't find anything else closer to the star, like conclusive results closer to the star. We couldn't find anything else far away from it. And there's also some material shielding the inner disk from Matisse results. So we posited the idea that maybe there is some kind of cloud of dust grains at the bottom of this CO outflow. Or if that is the case, perhaps there are more knots closer, but there may either there's too much scattering or they're too faint to be detected yet. And I'll leave you with my conclusions just to summarize again that what we've seen from Matisse is we're looking very close to the inside the disk, inside the mid-infrared emitting region. It's quite compact, which is typical now what we find for FUors. There are no crystalline silicates. There is some kind of dust shielding material closer to the center of the disk. While from the IFU, we see an emission line not farther out. It's a jet-like signature of about 5,000 years ago. And we want to go further again and look closer into that source. We're going to go and look at it with other instruments and try to figure out what's happening closer to the star again. And if there are any more questions, I'm happy to take them. Thank you.
I don't know if you can hear the claps, but we've thanked you. Any questions for Claire? Any questions? I had a question, actually. So I was wondering, and apologies if you already said this, compared to when V900 Mon went into outburst, is that not associated, like the distance and how quickly it's moving with that outburst timescale at all?
Oh, so that happened in the 90s. So let's say about 30-something years ago, more or less, or perhaps a bit earlier. And we tried to look to trace this back closer. So they would have been a few milliarc seconds in terms of the instruments we're using. So one or two pixels away. And we couldn't resolve something like that. It was very difficult because it's a very bright source. Yes, perhaps we need to use something else to target this one.
Sure, that makes sense. Any questions? All right, we have one.
So you need some extra extinction of the inner disk, right? Is that
Yes.
right? Shouldn't that show up in the spectral energy distribution at short wavelengths? Or, you know, I mean, is it consistent? Because you know, you're saying you needed some extra extinction, but of course that would affect. You know, that would make the star the disk look, you know, even more extincted. I'm just trying to, right? You know, because if you're affecting the silicate feature, you're also affecting all the emission shortwave wavelengths in a set. So is there some kind of test you can do of that?
One of the things I found is that perhaps the measurement we got is too low, because there's been a comparison between the near infrared spectrum and that FUori, and it even gives an even higher number, so about 13. We've also tried to run a couple of models for an accretion disk model to simulate the SED, and we get an extinction of about 8. That is combined interstellar and circumstellar. So in a way, perhaps it's consistent, but what I need to just try to repeat this whole experiment to see if I'm actually right in the beginning. So why would I have such a high extinction towards nearly pole-on targets? So I need to hide part of the disk. That's why we thought, like, if you need to hide only a part of the disk, perhaps this is what was it, the bottom of the CO outflow, or perhaps not. So I'll be happy to go back and have another look at it.
All right, we have time for another question, if there is one. If not, let's thank Claire again, and we'll get our next speaker.
Thank you.